Hi, this is Dr. B, and we are continuing Lab 3.1, Introduction to Ohm's Law and Circuits Remote Lab. We are down here in part 2 where we left off last time, and we are going to write some rules to describe how patterns of current and voltage in a circuit relate to the structure of the circuit. So how can we invent some ways that we can figure out, or we can make a good prediction about guessing the number of amps in a particular part of a circuit and the number of volts? We'll need to measure current and voltage in multiple places on several different circuits. So current here is measured in the ammeter. And you can see the current flowing in this circuit right here is 0.09 amps. And then to measure volts, we use the voltmeter here. And we have to measure voltage between 2 points. And it's measuring the difference, or how strongly the electrons are kind of pushed through this circuit. So we're going to have a bunch of circuits here. And we're going to look at the differences between the circuits. We're going to build these circuits. We're going to measure amps and volts into these circuits, and then we're going to compare them, compare the measurements of volts and amps. I've done a lot of the work for you for 12 and 13. Let me build those circuits so you can build them too. And you're going to have to do number 14. So I'll show you quickly how to build a circuit here. You want to grab a battery from the left-hand side. You can grab a bulb. We'll build this one, a simple circuit down here. You can just put a wire straight to the bulb and straight to the other side of the bulb. There's 2 connection points for the bulb. Don't put both the wires on the one connection point, or bad things will happen. So here's a very simple circuit. We can go over here to the right side. We can grab an ammeter, bring it over, and measure current anywhere we want. 0.9, 0.9, 0.9, 0.9. So it looks like in a simple circuit with just one bulb, the current is the same everywhere. Let's see about volts. So we can measure a voltage across the battery. We're going to see that that's 9 volts. We can measure it across a bit of the battery and the circuit. We can measure it across the light bulb. But if we measure it just in the wire, it's nothing, there's no electromotive force in the wire. It's all in the battery and in the bulb, pushing those electrons around. So that is a simple circuit. You can build it really easily. You're just connecting the wires to the bulb and the battery, and all that stuff is on your left here. So I built a simple circuit. All the measurements were 0.9 amps, and all the volts were across the battery and the bulb were the same. And I put 0 volts. There were 0 volts flowing in the wire. Now, if we make a series circuit, we can check out what that looks like. A series circuit has 2 bulbs, or 2 sources of resistance. I'm going to go over here, grab a light bulb from my toolbox, grab a wire. Now this is a complete circuit. Electrons can make a circle or a complete path around. Anything that makes a complete path for electrons is a circuit. We have 2 bulbs now, and let's see what the current is here. Last time it was 0.9 with our simple circuit with one bulb, and here it's 0.45. So it's half as much. Let's check out the voltage. So it's half the voltage on each of the bulbs. And across the battery, it's the same. So it looks like in our series circuit, it's kind of splitting everything in half. It's splitting the voltage in half, and it's splitting the current in half if there are two bulbs in the same circuit. That might be a good rule to write down. If you have a series circuit, everybody has to share. A good analogy might be everybody living in the same household, which is kind of similar to being on the same circuit, has to share everything in the house, like ice cream and towels and bathrooms and kitchen table, and you know what it's like. If you have siblings, life can get a little crazy. You gotta share, 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 share. Now let's build a parallel circuit. And we'll see how that might be a little bit different. Let's take this apart a little bit. I'm going to move my ammeter and my voltmeter out of the way. Now a parallel circuit's a little bit different. If I want to take my circuit apart, I can just click on things and kind of cut them. Let's make that go over there. I'm going to make it look like the picture in the lab. So we still have two bulbs, but they're connected in very different ways. Instead of sharing the same circuit, instead of being in the same loop, there's going to be separate loops for each bulb. So we'll make a separate loop out here. We're basically kind of building two separate boxes, or if you want to think of it as two blocks. Bring that corner in a little bit. Straighten out my battery. So you can kind of think of this as maybe having two friends who live in the same neighborhood. One lives on one side of the block, one lives on the other. You can travel to one, or you can travel to the other friend. If the road to one friend gets blocked, you can still travel to the other friend. Let's hook this friend back in. If the road to this friend gets blocked, you can still travel to the other block. So these two bulbs are parallel. They have independent ways the electrons can travel to them. So that makes parallel circuits a little bit different than series. If one of the bulbs burns out, the circuit for the other circuit will still work. The one path will work if the other path is blocked, if the bulb burns out or the wire gets cut. And a lot of circuits are built as parallel circuits. A lot of circuits in your house are parallel because if this light burns out, we don't want everything else in the house to go down. So now let's measure the current here. The current here is 0.9, the current here is 0.9, so they're not sharing like the series circuit. The series was 0.45 and 0.45, and we have 0.9, 0.9, and oh, look at over there, it's 1.8. So these guys are basically 0.9 plus 0.9 equals 1.8. They're kind of sharing it in a different way. But they both have the same, but it's a different number. Now let's look at volts. It's 9. It's 9 across that light bulb. It's 9 across that light bulb. So it's 9 across all of the light bulbs. So the voltage is the same. The amperage is different in a parallel circuit. So all the places I took the voltage here in a parallel circuit, it was the same. The current was different. Near the battery over here, it was 1.8, but near both bulbs, it was 0.9. Now we have a complex circuit, and you can figure out how this compares to parallel and series circuits. I'll help you build it, and we'll kind of show you how it works. So here's a parallel circuit. There are two separate loops. There's a loop here for this bulb and a loop here for this bulb. That's a straight up parallel circuit. But now we're going to complicate things a little bit. We're going to make a series circuit out of part of this. Let's grab a light bulb here. So it's called a complex circuit because it's a little bit of both. It's parallel, and then in the parallel circuit, there's a series circuit right here. So now let's check everything. Let's check the current. The current at these two light bulbs, they're splitting the 0.9 that this light bulb formerly had by itself. This light bulb is still 0.9, and this part is 1.35. That's interesting. Let's check the voltage. So there's 0.45 there. There's 0.45 on these two light bulbs. So they're kind of splitting the voltage that was formerly for just one light bulb. And now over here, it's still 0.9 over here for this light bulb. And the battery is still 0.9. So even within a parallel circuit, if you put a series circuit in, it's going to have to start sharing the amperage that would be for a single bulb. These two bulbs are sharing or splitting the amperage that was formerly just for this bulb, or just for this bulb actually. So the simple answer is that a complex circuit is similar to both of them. It's basically a parallel circuit, and it's a series circuit. It's a series circuit right here within the parallel circuit, and this is a parallel circuit right here. So that's part of the answer to number 14. A series circuit, how we would compare this, these bulbs have more amps. They're splitting the 1.8 amps coming out of the battery. And these bulbs have 0.45 amps. So these bulbs would be brighter. Also, if one of these bulbs goes out, the other one will stay lit. That will not happen here. If one of these bulbs goes out or gets disconnected, then the whole system has to go down. So, number 15, compare the patterns you see in the series circuit to the ones you see in parallel and complex circuits. So write rules about voltage and current for each type of circuit. So let's start with series circuit. Go up and look at our numbers. So they're splitting the amps and they're splitting the watts. They have half as, compared to a simple circuit, you split the amps and the watts, or the volts, excuse me, between the bulbs. So you have to divide all the amps going through, get divided by 2 for those 2 different bulbs, as well as the volts. That's a rule for the series circuit. For the parallel circuit, each of these is 0.9, and then you add the 2 amps here. Or sorry, for parallel. Let's make that nice and neat. We can just generally say more current near the battery, 2 times as much as each bulb. Let's go look for volts. Looks like the volts were the same across the whole circuit. So for the complex circuit, kind of both rules apply. If there's 1.8 amps coming out of the battery, you split those amps in 2, one for each of the circuits, and then because these bulbs are in series, they have to split that again between them. So the current is divided in half for each circuit. If there is a series circuit, then as part of the parallel circuit, the bulbs on the series circuit have to share current. And they split the amps. You split the half. So each has half as many amps flowing into it. Okay, predict your rules above in order, the order of the light bulbs in these circuits from brightest to dimmest. Some bulbs might be the same brightness. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 bulbs. And you should order them in a way that goes from brightest to dimmest. And you can just put the numbers in order. Like if you think 3 will be brightest, and then 6 will be the next brightest. Those are not the right answers, so don't take mine. Just make an informed guess. Look at those circuits and try to think about how the amps are going to be split up between those bulbs. And also consider how many bulbs are there. That's also a consideration. If you have to split a cookie with 3 people, you're probably going to get less than if you don't have to split it at all. So write those in order from brightest to dimmest, and then build the circuits. You should be able to use the parts that you have in the simulation to build all of those circuits. It'll take you a little bit, but it's okay. It's good practice. And then you can measure with the ammeter and the voltmeter which ones are brightest. The most current is going to result in the brightest bulbs. So you can use the ammeter to help you discover which ones are going to be brighter. Did your rules that we made in number 15 help you figure out the right brightness, the correct rank the brightness? Otherwise, you should go back and make some changes to our rules. Did you use any meters to help you make your list? If so, explain why. Well, I'll give you a hint here. I would use an ammeter because bulb brightness is one thing. We can just qualitatively, we can describe the light brightness between all these 3 bulbs and compare it qualitatively. But I would like to know quantitatively how much current they're getting. So I would use an ammeter, this thing here that measures current, to show me how much current they're getting, because that's directly related to how bright they are. If you're getting less current, you can see the shine or the rays coming out of this light are about half as big as this one. So these bulbs aren't as bright because they're only getting about half the current. If you want to make a flashlight and you have 2 batteries and a light bulb, predict how you would hook them up to make the brightest flashlight and why. So we have 2 batteries and a light bulb. You can, let's clear our circuit here. There's an orange button in the corner here we can use to clear everything. If we want to use 2 batteries, we could put them both in the circuit in different places, kind of put the bulb between them. Oops, that's not what I wanted to do. Actually, let's just get rid of that. So we could just connect everything up as a big loop. I seem to have crossed my wires here. There we go. Well, that's not going to work. Oh, because I have them negative to negative. That's no good. It's like putting your batteries in the wrong way. So that looks pretty good. That's pretty bright. I can measure how bright it is by checking the current. You can grab my ammeter over here on the right and see just how much current it's getting. 1.8. That's awesome. The other thing we could do is kind of do it like flashlights do, and we could line these up We could connect our batteries and see if that makes a difference. 1.8. Okay. You can mess around and see if you can make something brighter. Build some circuits, check your answer, insert images. And then you're done. Put it in the assignment folder. Put it in the assignment folder, and so you can get some points. Thanks so much for watching. This is Dr. B signing off on Lab 3.1. Introduction to Ohm's Law and Circuits Remote Lab. It's worth 93 points, so make sure you get it done.